Happy Chinese New Year. I'm really surprised that you guys are here, and I'm not surprised that a lot of people are not. So last session, we talked about how to solve recurrence relations. And there's just one thing that remained, and I want to go over it this session, and this is the master theorem or the master method. And this is basically a formula that you can memorize whenever you have recurrences of a particular form. And I've just copied this from the CLRS book. So if you have a recurrence of this form, T of n is A times T of n over B plus F of n. So this is a kind of maybe divide and conquer algorithm that takes an instance of size n, and it breaks it down into A instances of size B. And then after solving those instances, it spends F of n time to merge the solutions and find the solution for the original instance. Okay. So whenever you have this kind of recurrence, and by the way, here in n over b, you can also have floor of n over b or ceiling of n over b. That doesn't really matter. You always have these bounds. Now, how do we actually get these bounds? It's just the process that I showed you in the last session. So you just draw a tree, and based on that tree, you can guess these bounds, and then you can use induction to prove. So the proof is actually in the book, and I'm going to give you the proof on Canvas. But this is pretty much what you have to memorize. So, and I promise this is the last thing you have to memorize in this course. So generally, we want to compare two things. We want to compare this function f with n to the power of log of a in base b. Okay. So if f is much smaller than n to the power of log of a in base b, which means that it's O of n to the power of log of a in base b minus epsilon, then the answer is just n to the power of log of a base b. On the other hand, if f is much larger than that, then the answer is f, but you also need some side conditions. So remember the side conditions. And finally, if f is exactly theta of n to the power of log of a in base b, then you just get a factor of log n in the end. So you just get n to the power of log of a base b times log n, or otherwise we can also call this f of n times log n. Okay. Now, the proof is exactly like the things that we proved in the previous session. So you just draw a tree. You have at the root an instance of size n, and you're dividing it into A instances of size n over b. And then you talk about the total cost in this tree, and also like the height of the tree, the cost at every level, and so on. Okay. Now that we're done with this, let's go back to our sorting module. And today we want to talk about lower bounds on sorting. So remember, I told you that the algorithms we've seen for sorting already, merge sort and also heap sort, are actually optimal asymptotically in the sense that they take O n log n time, and I said it's kind of impossible to take less than n log n. And I'm going to show you why that's the case, and then I'm going to show you a linear time algorithm for sorting. So first of all, we have to say what kind of algorithms we want to look at. And we want to look at comparison-based sorting algorithms. Okay, so what's a comparison-based sort? It's a sorting algorithm that wants to sort, let's say, an array of elements. And all it can do to get any information about the elements in this array is to compare two elements. So that's all your algorithm can do. Your algorithm can take two different elements and ask which one is bigger. And let's assume that we don't have ties, okay? So I have some array, and it's not necessarily an array of integers, but it's just an array of elements. So I have an array A of n elements. This is my input. In the output, I want to sort A. So I want to print a sorted permutation of A. But let's say I cannot really access the elements of A. All I can do is ask questions about them. Give two elements and ask which one is bigger. Okay, that's the only available operation. And of course, I can have my memory. I can keep track of what the results of the previous operations were and all of those things. But crucially, I cannot really read the contents of the array. I can only compare the contents of the array. Okay. Now, if you think about it, this is enough for merge sort. If I wanted to do merge sort, I didn't have to actually go and look into the elements of the array A and ask what is the type of this element? Is it an integer? Is it, I don't know, a float, something else? I didn't care. As long as I could compare them, I could do merge sorts. The same thing happens for heap sort. If I want to create a heap of elements, I always want my maximum element to be at the top. I always want every element to be bigger than its children. But that's just comparison. I don't need to actually read the element. So both merge sort and heap sort are comparison-based sorting algorithms. Okay. Now, here's the thing. I want to prove a theorem. I want to say that any comparison-based sorting algorithm has to take at least n log n time. So this is our theorem. Any comparison-based sorting algorithm must make at least n log n comparisons, must make omega n log n comparisons. So if I have to do this many comparisons, of course, my time is also at least n log n, because I'm doing comparisons, maybe I'm doing some other thing, maybe I'm remembering some things, doing some other calculations. But anyway, if I need at least these many comparisons, my time cannot be less than this. So if I prove this, I have basically proven that you cannot have a comparison-based sort that is asymptotically faster than merge sort or heap sort. Merge sort and heap sort are optimal. Okay, so how do we prove this? Well, we're just going to do the same thing as before. We're going to draw a tree. In this course, we're always drawing trees. So here's the thing. I create a tree, and every node of this tree is going to correspond to the information that my algorithm has. Okay, so my algorithm has got some input, and this input is just n elements. And at the beginning, my algorithm has no information at all because it hasn't made any comparisons. So I show that with a node in my tree, and actually this is the root node. So this corresponds to the state of my algorithm where I don't know anything. I haven't asked any questions about the input yet. Now, here's the thing. I want to prove this theorem for any algorithm. So I don't get to fix the algorithm. I have to say, suppose someone else has given me an algorithm, and I have to reason about any possible algorithm. So I'm going to say, well, this is a comparison-based sort. So any comparison-based sort, when starting with no information, the way that it gets information is by making some comparison. So it's going to do its first comparison, maybe comparing, let's say, item I with item J, right? Now, this comparison can have two different results. Either item I is bigger or item J is bigger. So no matter what my algorithm is, this root node is going to have two children, right? And this corresponds, so let's say this one corresponds to the case where the answer to the first question was no, and this one corresponds to the case where the answer to the first question was yes. And the first question is based on the algorithm. And the algorithm is comparing two elements. So it's asking, is this element larger than that element? Yes or no? Okay. Now, of course, no matter what my algorithm is, it's going to continue asking questions. So if I'm in this state, the algorithm is going to again ask a question. And based on that question, it's going to get some information. And then I'm going to go to two new states of information. So every state of my tree here, again, models the information that the algorithm has based on all the questions that it has asked until now. And of course, this continues until the algorithm terminates. And when the algorithm terminates, it has to output a sorted permutation. It has to output the sorted version of the array. So I have this binary tree, and it's binary in the sense that any node that is not a leaf has exactly two children. But it's not like all the leaves are at the same level. It might be that, for example, this one has two children, because in this case, the algorithm asks questions, but maybe in this case, the algorithm already outputs something, right? So it depends on my algorithm, and I don't know what the algorithm is. Now, so I have a binary tree, and this is the binary tree of the knowledge of the algorithm. Now, the question is, what is the runtime of my algorithm? And let's say that I'm doing this on an instance of size n. Okay, so my input size was n, right? If someone gives me this tree, and it's a huge tree, it's like every possibility in my algorithm, everything that can possibly happen in the execution of it. How can I get the runtime of the algorithm, or the number of comparisons of the algorithm in the worst case? It's just the depth of the tree, right? Because my algorithm always outputs something when it gets to a leaf. And in order to get to a leaf, it makes a number of comparisons, but the number of comparisons is just the distance from the root to this leaf. So if I want to find the worst case number of comparisons, that's just going to be the depth of the tree from the root to the lowest possible leaf. Okay. So basically, I want to prove that the depth of this tree is omega n log n, because the depth of the tree is just the number of comparisons of the algorithm. So this is what I want to prove. We want to prove that the depth of this tree, let's call it d, is in omega of n log n. Okay. But I don't have a direct way of talking about the depth, so let's instead talk about our leaves. How many leaves does this tree have? N factorial, yes. So you see, I have my original array, and my original array can be unsorted in any of the n factorial possible permutations, right? So when I'm writing some permutation of the original array, I might have to undo any of the n factorial ones. So there are n factorial possible outputs, right? So again, when I'm starting my algorithm here and I have no information, I don't know which of the n factorial possible permutations of my original array I have to output. And if my algorithm is correct, it has to be able to output all of them. So this means that I should have at least n factorial leaves. I might have more than n factorial leaves, because maybe there are two leaves that are outputting the same permutation. But I should be able to create all the possible permutations, so I should have at least n factorial leaves. Okay? So this proves that the number of leaves in this tree is at least n factorial. Okay. So what does this say about the height of the tree? If I have a tree with n leaves, its height is at least log n. It's a binary tree. Now I have a tree with n factorial leaves. So its height is at least log of n factorial. So that's what I know. I know that the depth or the height of my tree is at least log of n factorial. Or actually, let me write it with the omega notation because that's what we prefer. It's in omega of the log of n factorial. Okay. But we've seen before that log of n factorial is basically n log n. So this is also the same as omega of n log n. I'll do that proof again for you, but I just want you to see the overall picture here. So the overall picture is that I created a tree which shows all the possible behaviors and knowledges of my algorithm on inputs of size n. And I said that this tree should have at least n factorial leaves. Because it has at least n factorial leaves, its depth or its height should be at least log of n factorial. But the depth is just the number of comparisons that my algorithm is performing in the worst case. So my algorithm has to perform at least log of n factorial comparisons in the worst case. So my runtime is going to be at least omega n log. Okay. The only remaining part is to show that log of n factorial and n log n are basically the same except for some constant factor. And I did this in one of the previous sessions, but let me just do it again really fast here. So if I want to write what log of n factorial is, log of n factorial is just log of 1 plus log of 2, so on, to log of n. Okay? Now, here's the thing. I have n logs here, and all of them are at most log of n. So log of n factorial is definitely less than or equal to n log n. Right? I have n terms, all of them are less than log n. So this shows that log of n factorial is less than or equal to n log n. But if it's less than n log n, it's also in the O of n log n. But now to show the other side, we said that we'll look at these logs until log of n over 2, and then the logs after that. And then we just say, forget about these small logs. Forget these ones. Let's just sum up these ones. Right? I have n over 2 of them, and each one of them is at least log of n over 2, which is log of n minus 1. So this shows that the sum is omega of n log n. It's like n minus 1 times log of n minus 1, but who cares? That's just omega of n. So this shows that log of n factorial is also in omega of n log n. And basically this means that log of n factorial is in theta of n log n. Okay. Great. So now we finally have this theorem. We filled in all the gaps. So it's impossible to have a sorting algorithm based on comparisons that makes less than n log n comparisons. Asymptotically less. Okay. But then, of course, the part that is interesting in this theorem is that any comparison-based sorting algorithm has to make these many comparisons. What if we can have a sorting algorithm that sorts something not based on comparisons, but based on something else? Maybe you have some particular knowledge about this array A that lets you do something better than comparisons. In that case, you might be able to sort the array A in less than n log n time. Okay. Now, here's a very simple example. Let's say I give you an array of integers. So this is my problem. My input is an array A of n integers. Okay. But let's say that I tell you that all of these integers are at most 100. Okay. So these are integers, let's say, between 1 and 100. And as the output, I want you to print a sorted permutation of A. Basically, just sort A. How would you do this? Well, of course, I can use my comparison-based sorting algorithms. I can just use merge sort or heap sort or a bunch of other sorts that we will see soon. And I can sort them in n log n. But here I know that all of my numbers are small. I know that I only have integers between 1 and 100. So I can just count how many times each integer is appearing in my array, right? So I can start from the beginning of my array and just count how many ones do I see, how many twos do I see, and so on until 100. And after that, based on that, I can just print out each number by the number of times that it appeared. So this is, can you believe it? It's called counting sort. Okay. So here's counting sort. The simplest possible algorithm for sorting. So I just keep a count. Let's say whatever, 150. And then I read my number n. And I just say for I from 1 to n, read one of the numbers of the array. I'm not even going to keep the array, who cares? And increase the count of this number. Just remember that you've seen this number. And then at the end, just go over all of the numbers from 1 to 100. We said all of our numbers are from 1 to 100. And print it as many times as its count. So for j from 1 to count of I, just write I. That's it. Let's say I have 5 numbers, 1, 2, 3, 4, 5. And as you see, it's sorted. Now, of course, this is going to take linear time. It's going to take O(n) time. Right? Because this first 4, it's just going from 1 to n, and it's doing a constant amount of work in every iteration. So the first 4 is taking O(n) time. This one, it's just doing a constant number of iterations. And this one is only going up to the count of I, which can be at most n. So again, this one is also O(n). Yeah. So to be more specific, if instead of saying that my numbers are between 1 and 100, I had some number m here, my numbers are between 1 and m, then my runtime would just be O(n) plus m, where n is the number of numbers and m is the maximum number. Right? Okay. So this is counting sort. And it's fine, but I mean, what if I have an array of integers between 1 and let's say 2 to the power of 32 or 2 to the power of 64? Let's say I have actual integers that I'm saving in my C++ code, so I can have 64-bit integers, right? So what can we do then? So my input is, again, exactly the same as before. I have an array A of n integers, but my integers are, let's say, between 0 and 2 to the power of 64 minus 1. Okay, so these are the numbers that I can save in an unsigned integer in C++ on a 64-bit system. Okay. Now, in this case, I don't want to just use counting sort. Because my m is 2 to the power of 64 minus 1. That would take a really long time. But here's a very simple idea. What happens if I look at every digit of my numbers separately? You see, this is, again, another operation that is very different with comparisons. I'm not doing comparisons. I'm actually looking at the digits in my numbers, right? So let's say I have a bunch of numbers, I don't know. Let's say one number is 5, one is 12, one is 16, one is 20, one is 51. Okay. Maybe I can make this one into 105. It's a bigger number. Okay. So let's say I have these numbers and I want to sort them. Well, first of all, I make them all of the same length. So let's say I have a 0 here, just to make sure they all have the same length. And now let's say that I just sort them based on their last digit. And to sort based on the last digit, I can do something like counting sort, except that I have to also keep track of the rest of the digits. So instead of just having a count, I'm going to have an array. So I'm going to create an array of all the numbers whose last digit is 0, another array of all the numbers whose last digit is 1, and so on. And using that, I'm going to sort everything based on the last digit. So this is what I'm going to do. I'm sorting based on last digit. So the smallest last digit is 0. So I will have that number first. Then I have 1. So I put this one. Then I have 2. And then I have 5, 1, 0, 5. And finally, I have 6. So the last digit is now sorted, but of course, the numbers are not sorted themselves. But now let's say that I sort based on the next digit. But if this digit is the same, for example, it happens here 1 and 1, then I keep the same order that I had before. Okay. So now I'm sorting based on the second digit. Okay. So the smallest one is 0. So I'll get 105 as my first number. Then the next smallest one is 1. So I can put 012 or 016, but I keep the same order that I had before. So I will have 012 first, and then I'll have 016. Okay. Then I have 2, so 020. Then I have 5, 051. Okay. Now, if you ignore the first digit, and if you only look at the last 2 digits, then all the numbers are sorted. Right? My only problem is that the first digits of my numbers are not sorted now. So I'll do the same thing. But now this time I'm going to sort based on the first digit. And again, if 2 numbers have the same first digit, I'm going to keep the same order that I had before. Okay. Or actually, well, I have to. Okay, let's do this first digit. I have to go to the next line. So I have a bunch of zeros and I write them in the same order as before. So I have 0, 1, 2. I have 0, 16. I have 0, 2, 0. And I have 0, 5, 1. And then I also have a 1. So 1, 0, 5. And at this point, my numbers are sorted. Great. So what is the idea here? The idea is very simple. I say after every iteration, let's say after the ith iteration, if I only look at the last I digits of my numbers, they are in a sorted order, right? So after the first iteration, the last digits are sorted, 0, 1, 2, 5, 6. After the next iteration, the last 2 digits are sorted, 0, 5, 1, 2, 1, 6, 2, 0, 5, 1. Okay, so it's like 5, 12, 16, 20, 51. And after I do 3 iterations, all 3 digits are included and everything is sorted. And you can easily prove that this works by induction. It's like if here I know that the last 2 digits are already sorted, of course, the numbers that have the 1 at the beginning are going to be bigger than the numbers that have a 0 at the beginning. But the numbers that just have a 0 at the beginning, the rest of the number was already sorted, so I have to put them in the same order as before. Okay, so that's the idea, and this is what we call Radix sort. Now, of course, if I want to do it for integers in C++, I wouldn't do it in base 10. We're computer scientists. I'm going to do it in base 2, right? So let's do it in base 2. And let's actually create, let's call it rsort.cpp. This is going to be Radix sort. And let's say all of my numbers are 32 bits. So I'm going to have some number n. And then I also have my array A. Let's say I can have at most 10 to the power of 7 numbers or something like that. And I have my array A. And I just read everything into A. And let's say that I don't have negative numbers. Let's say I only have unsigned integers, because if I have negative numbers, all the negative numbers are smaller than all the positive numbers, and then I can sort them separately, right? But let's say all of my numbers are non-negative. Okay, so here's what I want to do. I want to sort this array, first of all, based on the last binary digit of all the numbers in there. So basically, I want to put the even numbers first and the odd numbers after them. Okay. Now, I can use a vector, but I'm a bit unhappy with using vectors. So instead, I'm just going to create my own array. I'll show you why soon. And it's just going to have the contents, which is of size max n, and it's going to have some number n. And here's the thing, I want something like a vector, but the problem I have with a vector is that every time that it gets bigger, it starts allocating memory again. That wastes a lot of time. I don't want to do that. I just want to create something like a vector, but I want to already allocate all of the memory at the beginning. Okay, so I have this weird array that I have here, and I can push into it. Actually, let's say push. And what it does is that contents n becomes x and n increases. Again, don't do this, but I always do this. I like this. And then let's say I have a pop, and my pop just decreases n. So n is basically the number of elements that I have, and it's initially 0. And of course, I can say I do pop only if n is greater than 0, otherwise don't pop anything. And push, I don't care. I think it's fine. So I'm creating this simple array for myself, and I'm going to have this array A. And of course, here I have to say a.contentsI. So other than my array A, I want to also have two other arrays. I'm going to call them Z and O for 0 and 1. Oh no, that O looks like 0. Okay, so I'm going to just call them 0 and 1. Okay. And let's say that I also have clear, which just sets n to 0, clears everything in my array. And okay, here actually let me push. So I say I read some number x, and I say a.pushx. Okay, now I want to start going over all of the elements in A, and I want to just look at their last digit. And the ones that have 0 in their last digit, I'm going to put them in 0. The ones that have 1, I'm going to put them in 1. Okay, so I'm going to say for every I from 0 to n. Actually, sorry, let me also have a size here, which just returns n, because I prefer to write it like this. Okay, for every element in my array A, I'm going to say if the last digit, if I modulo 2 is 0, put it in the array 0. Okay, so 0 dot push, sorry, if AI, if the ice element, actually I have to do this, then put it in 0. Otherwise, put it in 1. Okay. So at this point, I've just partitioned my elements based on their last digit. But I don't want to just do this for the last digit. I want to do it for 32 different digits. So let's have another for loop around this, where I say for digit from, let's say, 0 to 32, for every digit, I'm going to do this. But here, actually, I want to give this a name. Oops, let me erase this, sorry. So I want to just say X is the ice element in my array. And then I want to say if the digit number D of X is 1, put it in the array 1, otherwise put it in the array 0. How do I get the D's digit of X? I just take X, I shift it to the right D times, and then I want only the last digit of that, so I take that modulo 2. That gives me the D's digit of X. So if this is 1, put X into the array called 1. Otherwise, put X into the array called 0. Okay, now I've divided everything based on this digit. Now what am I going to do? I'm going to first clear my array A, and then I'm going to put the zeros first, and then the ones. So for every I from 0 to 0 dot size, I say A dot push 0 dot contents I, and then I'm going to do the same thing for 1. And then I have to clear my 0 and 1. You see why I didn't use a vector. I didn't want to just allocate and deallocate memory all the time. Okay. That's it. That's my Radix sort. And I'm using base 2, and I'm using up to 32 integers. So it should work. Let's say I have 5 numbers. Let's give the same numbers as here: 105, 12, 16, 20, and 51. Oh, and I forgot to print it. Okay, at the end, I have to print everything. Okay, 12, 16, 20, 51, 100. Now, what is my runtime here? How much time am I spending? Well, I said 64 here, but in the implementation, I did with 32 bits. But let's say I have a fixed number of bits, right? If the number of bits is constant, then you see that for every bit, I'm spending O(n) time, right? So I'm just going over my array A once, and then I'm going over each one of the arrays 0 and 1 once, but 0 and 1 together have the same length as A. So this is O(n). So if the number of digits is fixed, the total runtime is linear. It's just O(n). If you want to also care about the number of digits, and if you want to say I have D digits, then the total runtime is going to be O(n) times D. Right? Where D is the number of digits. Now, which one do you think is faster, Radix sort or merge sort? Well, it kind of depends, right? It depends on the number of digits that you have. And also it depends on your particular implementation and your particular CPU. Like maybe comparisons are much faster on your CPU than shifts, for example. So I cannot say for sure. And of course, it also depends on like how this D compares with log of n, right? So if you have a lot of numbers that are really short, then D might be much smaller than log of n. And then Radix sort would work better. But if you have a few numbers that are very long, then D would be larger. It's better to do n log n. But then the other question there is, if I have really long numbers, can I really compare them in O1? So you see, it really depends on your assumptions. You have to say what you assume you can do in constant time. What are your basic operations? Okay. But anyway, this is, at least for some numbers, a linear time algorithm. And you see, the reason I could get a linear time algorithm, let's say if my numbers are at most 2 to the power of 64, is because I wasn't doing comparisons here. I was doing things other than comparison. I was looking into the digits of these numbers. I was assuming that I have numbers and they have digits, and I can look into the different digits separately. So if I want to sort an array of, let's say, strings, it's not immediately obvious how I can use the same Radix sort. That's actually probably one of your homeworks. Okay. So that's it for the sorting part of this course. Now we're going to move forward and go to a different data structure. We're going to talk about binary search trees. Now, one important point before I start, this is parenthesized like this, okay? They're search trees that are binary. They're not trees for binary search, okay? They're binary search trees. Okay, so generally we use BST for binary search tree all the time. And this is a data structure that is kind of inspired from the same ideas that we've already seen for heaps. It's just that we have a different rule. So a binary search tree is, of course, a binary tree. So I have a tree that has a root, and every node can have at most 2 children. But unlike the case of heaps, this is not an almost complete tree. So it can have any shape. The only point is that every node can have at most 2 children. And a node might have only 1 child. It might have both children. Maybe it only has a left child. Maybe it only has a right child. All of these things are possible here, okay? So, and of course, at each one of my nodes, I'm going to save some value or some key. And the idea is that I have to have a rule about every node and its children. So in the case of heaps, I would say that the value at every node had to be larger or equal to the value at both of its children. Here, I'm going to do something different. I'm going to say that the left child should be smaller, the right child should be larger. So this is the rule in my binary search trees. It's that the left child of every node should have a value less than or equal to its parent. And it's the exact opposite for the right child. So the right child of every node should have a value greater than or equal to its parents. Okay. So let's consider this tree. Let's put some values in here to make it into a binary search tree. Let's say I have 5 here. So here I should have something less than 5. So I put 4 here. Here I should have something less than 4. Let's say I put 3, and here I have to put 4. Now 5, I put 6 here. I put maybe 5 here, and I put 7 here. Okay. But you see, this is not enough. I don't want to just say that the left child of every node should be smaller than it. I want to say everything in the left subtree should be smaller than this node. And the same thing for the other side. So instead of just saying the left child, I make it more demanding, and I say any node in the left subtree. So that means if I take some node, for example, I take this 5. What is its left subtree? Its left subtree is its left child and all of its descendants. They should all have values that are at most 5, less than or equal to 5. What is its right subtree? These nodes. They should all have values that are greater than or equal to 5. So here again, instead of saying the right subtree, I say any node. Sorry, instead of saying the right child, I say any node in the right subtree. So in this sense, I'm kind of having a more complicated thing than what I had for my heaps. But if you think about it, it makes sense, because in a heap, when I said that every node has to be bigger than its children, of course, it would also be bigger than all of the descendants. But here I want to say whenever I'm moving left, my value is decreasing. And whenever I'm moving right, my value is increasing. So it's not enough to say that by moving left, my value decreases, and by moving right, it increases, because maybe if I go from here to here, my value increases above 5. I don't want to allow that. I want to say everything that is to the left of 5 has a value that is smaller than 5. And everything that is to the right of 5 has a value that is larger than 5. Okay. Now, of course, our very first problem here is how to implement this, because I cannot use an array anymore, because now I don't have an almost full tree. All I'm saying is that it's a binary tree. Every node can have 2 children. So normally we would implement this with pointers in C++. Now, but before that, let's just go through some operations. What are some operations that we would like to do? Well, very much like the case of heap, let's first try talking about insertion. So let's say I want to insert something into my tree. Okay, so I have this operation, insert x, and basically this one adds the number x or adds the key x. It doesn't have to be a number as long as we can compare them to the binary search tree. Okay, let me copy my binary search tree from here. Okay, let's erase these. Oh, the eraser even erases the background. I'm always surprised by this. Okay. So this is my tree. Let's say I want to add a new number. Let's say I want to insert 10. How would you insert 10 in here? Well, I can start at the top, and I can compare 10 with my root. My root is 5. Since 10 is larger than 5, that means that I have to insert 10 in the right subtree of 5. Right? So I go right. I go to 6. I compare 10 and 6. I see that 10 is larger than 6. So I have to insert it in the right subtree of 6. So I just go to the right child of 6, which is 7. And then I see that 10 is larger than 7. So 10 should go in the right subtree of 7. But there is nothing there. So I just insert a new node. And I make 10 the right child of 7. That's inserting 10. Now, let's say I want to insert 5. This is a little bit more complicated. Because I see that I have 5 here. So I can decide to put the next 5 on the left or on the right. Right? It's equal. It can go in either subtree. So let's say I just break the ties in favor of left. I say I go to the left subtree. Then I see this 4, and I want to insert 5. So I have to insert 5 in the right subtree of 4. But 4 doesn't have a right child, so I can just create a right child for 4, and I can put 5 there. Okay. Let's do just one more. Let's also insert 2. If I want to insert 2, I start at 5. I see that I have to go left. I see 4, I have to go left. I see 3, I have to go left. But there is no left, so I just create 2 here. Okay. This is great. So this is my insertion. Now, how much time do I need to insert a new element? If I do insert x, how much time will it take? Log n. No, not necessarily log n. You see, I have to start at the top of my tree, and I have to go all the way down. So it's going to be O of the height of the tree. But I don't know that the height of this tree is log n, because I don't necessarily have a complete tree. It might be that my tree is just a path. So my runtime here is just going to be O of the height of the tree. I'm going to call it h, and h is the height of the tree. By the way, sometimes I call it depth, sometimes I call it height. They're the same. It depends on your point of view. Okay. Great. So that's how much time I need to do insert. But what if I want to do search? And by search, I mean that I give you some number x, and you should just return true or false. You should just tell me, is x in the binary search tree? Okay. So let me just copy this. Let's say I want to search for, and actually, let me change some of these numbers. I have so many 5s in here. Okay, let me change some of these numbers. Yeah, generally 5 is not a good choice for up there. So let's say 2, 3, 4. Let me put a 5 here. No, let me put a 10 here. Let me put a 7 here. Let me put a 12 here. Now everything here should be larger than 12. So let's say 100 here, 19 here, 200, and 201. Okay. So hopefully this is correct. Let's say I want to search. Let's say I want to search for 11. How would you search for 11? Again, I start at the top of my tree. I start at the root. I see that the root is 12. If the root were already 11, I would be really happy because I have found my number. But the root is not the number that I was looking for. So since this is not the number I was looking for, and since my number is smaller than the root, I know that I have to search in the left subtree. So now I go to the left subtree. I see a 7 here, which means that I have to go to its right subtree to search for 11. I go to the right subtree, I see a 10. which means I have to go to the right subtree again to search for 11. But there is no right subtree, so that means 11 doesn't exist, right? So if I search for 11, I would return false. Now, let's say I'm doing a search for 19. I start at the top. I have 12. I go to the right because 19 is bigger than 12. I see 100. Then I know that I have to go to the left because 19 is less than 100. And I go to the left and I just found 19. Because I found 19, I say, yes, true. 19 is there. Now let's say I'm searching for 12. If I search for 12, I just start at the root. I see that I have 12. I return yes. Let's say I'm searching for 7. I start at the root. 7 is less than 12, so I have to go left. I go left. I see 7. I'm happy. I found 7. Okay. So this is my search algorithm. Just start at the root and always go left or right based on the comparison of the value you're searching for and the value that you have at the current node. Okay. What is my runtime for searching? Yes. It's again, I called it H, right? Yeah. It's O of H. I switch between H and D all the time. So this is also O of H for the exact same reason as before, because I'm starting at the top and I'm just going through my tree. I'm going down until I cannot go down anymore or until I find my item. Anyway, I can go down by at most the height of the tree, so it's O of H. Okay. So inserting is easy, searching is easy. Let's say I want to delete an element. Okay. So we have to always make our lives hard. Let's say I want to delete an element now. This is like, let's call it delete X. Well, let's not call it delete because that's a keyword in C++. So let's say remove X. Okay, and what remove X does is that if X is in the binary search tree, remove it. Now, here's the part where things get a little bit complicated, because what if I have several copies of X? Do I have to remove all of them or just one of them? Now, in general here, I mean that if you have several copies of X, you have to just remove one of them. Okay? But a lot of the times in our binary search trees, we actually do not allow repeated numbers. And that makes life much easier because then there is only one if there is, and you can remove it. Okay. Let's say this is my binary search tree. And let's say that someone is asking me to remove 201. Okay. So in order to remove this number, I have to first search for it. So I do a search, and if this number doesn't exist, great. It's not there, I don't have to remove anything. But in this case, actually, I start at the top. I'm searching for 201. So from 12, I go to 100. Then I go to 200. Then I go to 201. So I see that this node has to be removed. But I'm really lucky here because this node is actually a leaf. It doesn't have any children. And because it doesn't have any children, I can just erase it. Right? And everything works out. I still have a valid tree. So that was the simplest case, the case where my node has no children. Okay. But let's go back to the original tree. What happens if instead of 201, I wanted to remove 200? If I want to remove 200, I start again searching for it at the top. I see that I have to go right. And then again, I have to go right. And I find 200 here. But now 200 has one child. So I can't just erase it. Because if I erase it, now my tree is no longer a tree. I have two different connected components. Right? But I can erase it and I can put its child in its place, right? So I can make the child a child of the parent. Okay. And this works out because you see here, when I had 200 here, 201 was in the right subtree of 100. So it was definitely bigger than 100. So now when I'm removing 200, I can make 201 the right child of 100 because it's bigger than 100. And even if this 201 had some other children and descendants, everything would work out because all of them would be larger than 200 and so larger than 100. So this case was also easy. The cases where I had no children or I had only one child was easy. Of course, the case where the number doesn't even exist, that's the easiest thing. You don't change anything. Now let's do the bad case. And the bad case is when my number actually has two children. So let's say I want to remove 7. So I start at the top. I first search for 7 and I found my 7 here. Okay. How do you want to remove 7? Who should take the place of 7? Well, in this case, yes, but well, what if 10 itself had some children? So I can remove 7 here and just put 10 in its place. But this only works because 10 doesn't have any descendants. Let's say that 10 also has a bunch of descendants, maybe on this side, let's say 11. And on this side, let's say it has 9. Okay. So now if I want to remove 7, I can't just put 10 in its place because I have a binary tree. If I want to put 10 in the place of 7, let's just try this. Let's say I'm removing 7, right? I want to put 10 as the left child of 12. That's fine. But 10 already has 2 children. So where am I going to connect 3? You see, that's a problem. So I can't just delete things that have more than one child. Now, what do you suggest I do? And remember what we were doing with heaps. Remember, so in the heaps, we had kind of a similar problem. The problem was that the structure of our tree was fixed. I couldn't change how my tree looked like, but I could swap some of the elements. Now here, I have some flexibility on the structure of the tree, and that's why I could remove nodes that had only one child or nodes that had no children. But I don't have that much flexibility. I cannot just remove 7. So a really nice idea would be to take 7, swap it with something else, and then remove that other thing, as long as that other thing is easy to remove, right? So here, what can I swap 7 with? 9, yes. Any other options? I can also swap it with 4, right? No. Yes. Yeah. Okay. So here's the thing. If you look at these numbers from left to right, they're basically in sorted order, right? So I have 2, 3, 4, 7, 9, 10, 11, 12, 19, 100, 201. That's the property that I have in my binary search tree. If I just parse it from left to right, I'll get all of my numbers in the sorted order. Okay. So if I want to remove 7 and I cannot remove 7, I can always swap 7 with the next element in this order and then remove that next element. So what is the smallest element that is larger than 7? In this case, it's 9, right? So if I swap 7 and 9, let's do this. Let's put 7 here. Oops, wrong color. Put 7 here and 9 here. Now, I might have some violations, but I don't care because I'm removing 7. If 7 does not satisfy some requirements, who cares? I'm removing it anyway. So I remove 7. But the really important point is that 9 was the number right after 7. Right? So by changing 7 to 9, none of my other orders are going to be violated. Now, the other option I had was to look at 7 and just find the number right before 7, which is 4, and swap 7 and 4. Okay, that would also work. I could just swap 7 and 4, put 4 here, 7 here, and now remove 7. This is also a valid solution. So your choice. You can find either the next number or the previous number and just swap. Now, here's the question. Does this swapping always fix our problem? Because what if the next number itself has 2 children? Is that possible? Can I be in a situation where my next number has 2 children? No, because if I'm going from 7, let's say 7 has a left child and a right child, okay? And actually, here's the thing. If 7 has a left child and a right child, the next number after 7 is definitely going to be in the right subtree of 7, right? So I go to the right subtree of 7, which is in this case 10, 9, and 11. And then in this right subtree, I have to find the minimum elements. Now, if I want to find the minimum element, I know that as I go left, everything is decreasing. So finding minimum is super easy. Just always go left. So I keep going left until I cannot go left anymore. And that's my minimum. And of course, since I started here, it's only the minimum in this subtree. If I wanted my total minimum, I could just start at the root and keep going left as much as I could. Okay. Now, since this is the minimum element in its subtree, in the right subtree of 7, it means that it didn't have a left child, because otherwise I would just go to the left child, which would be smaller. So since it doesn't have a left child, it has at most 1 child. And I know that something that has 1 child can be removed. So I can just swap 7 with the next number after 7, and I can remove it. Now this number, it might have a right child. Maybe I had, I don't know, 9.5 here, right? And in that case, this right child would just become the child of its grandparent directly, right? So I would just swap 7 and 9. 7 comes here, 9 goes here. I delete the 7. I connect 9.5 directly to 10. So 9.5 becomes the left child of 10. Okay. But I can say the same thing about the largest element that is smaller than 9, right? I can just start at 9. If it has 2 children, then the largest element that is smaller than 9 has to be in its left subtree. I go to the left subtree, and in the left subtree, I find the maximum element. How do I find the maximum element? I just keep going right as much as I can. And when I keep going right as much as I can, at some point I get to a node that doesn't have a right child. So that's a node that I know how to remove. So I can swap and then remove. Okay, so removing was actually quite more complicated than the previous ones. But how much time does this take? So this is also OH, right? Because I'm first doing a search, and the search took OH. Now, if my search is unsuccessful, if the item doesn't exist, that's the end of my removal. If I find the item and it only has 1 child or no children at all, I just remove it in constant time. And if I find some item and it has 2 children, then I have to either find the minimum in its right subtree or the maximum in its left subtree. But finding minimum or maximum is also OH, because I'm just starting and going left as many times as I can, but I can go left at most as many times as the height of my tree. So every operation that I'm doing overall is going to be OH. So removing is also OH. But to solve the removal, actually, we kind of solved some other problems. So we solved the problem of finding the minimum. So minimum just returns the smallest element in my binary search tree. And this is also OH, because I just start at the root and I keep going left until I get to a node that doesn't have left anymore. And then maximum is also returns the maximum element. This is also OH. And of course, we use this maximum only on some subtrees. We didn't really use it in our entire tree, but that's fine. Like I can have this operation for the entire tree as well. Now, the other operation that is interesting is to just sort everything, right? So if I ask for sort, which means just output a sorted array of all the numbers in the BST, sorted list or array of BST elements. How much time do I need for this? So let me just copy this again. So let's say I want to print all of the numbers in this binary search tree in sorted order. How do you do it? Well, first I can just find the minimum and print the minimum. Then I delete the minimum. Then I keep doing the same thing. Just find the minimum, print it, delete it, and so on. But that would give me a runtime of O(n) times h, right? Can I do better than n times h? How would you do better than n times h? So here's the thing. Let's start at the root. And when I start at the root, what do I know? I know that everything that is smaller than the root is in its left subtree. So I have to first recursively print the left subtree in sorted order. Then I know that everything in the right subtree is bigger than the root. So I first print the left subtree, then the root, then everything in the right subtree. And it's just a recursive algorithm, right? So this is going to be my sort algorithm. Super easy. My sort does this. Well, it takes a pointer, p, and originally my p is pointing to my root. Okay, and here's what it does. It says if I have a left child, print my left child first. So if there is a left child, if p left exists, call yourself on p left. Okay, and then just print whatever you have in p. Print whatever value you have in p. And then if p right exists, recursively sort and print everything in the tree that is rooted at the right child. So basically, this is the way I'm going to start. I'm going to start at 12. And at 12, I see that I have to first print the left subtree. So I go to 9. Then I see that I have to print the left subtree. I go to 3. I have to print the left subtree. I go to 2. There is no left subtree. I print 2. Now I want to print the right subtree of 2. There is no right subtree. I go back in my recursion. I go to 3. I have already printed the left subtree. So now I print 3 itself. Now I print the right subtree of 3, which is 4, and so on. And I just continue this. Now, how much time does this take? Yes, it's O(n). Why is it O(n)? How can it be O(n)? Yes. Or actually, I would rather look at my edges, but you're right. You can also look at the nodes. You can just count how many times you pass every edge. right? So as I want to print, I start here, I go left, I go left, I go left, I print. I go back, I go right, I print. I go back, I print. I go back, I go right. Sorry, I go back, I print. The whole thing went away. Okay, let's do this again. I start at 12. I go left, 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 print. Go back up, print. Go right, print. Go back up, go up, print. Go right, go left, print. Go back, print. Go right, print. Go back, go back, go back, print. And okay, let's do the whole thing, whatever. Go right, go left, print. Go back up, print. Go right, print. And that's it. Go back, actually, go back. So if you look at this, I'm crossing every edge twice, right? And because it's a tree and it has n nodes, it has n minus 1 edges. And I'm crossing every edge twice, so that's On. Yeah, the other way of looking at this is to look at the nodes. So when I'm calling sort on my root, it recursively calls sort on the left subtree, on the left child, and also on the right child. But every child has a unique parent. So sort is called on each one of the nodes exactly once. But whenever I call sort on a node, I'm doing a constant amount of work other than the recursive calls. So again, it's On. Okay. So this is now On. So now we have a sorting algorithm, right? I can just start with an empty binary search tree and just insert all of my numbers into it. And then I can call this sort function here, which prints everything in sorted order. Now, here's the thing. My sort function works in linear time, in On. But my binary search tree is a comparison-based data structure. I'm not doing anything other than comparisons with my numbers. So the theorem that we had here actually applies to this sort. Where's the theorem? Yes. So I need at least n log n time. But my sort function is taking only On time, which means that if I'm inserting n elements into a binary search tree, I am forced to spend at least n log n time for the insertions, right? And of course, you can get that from here as well. So insertion takes OH time, but if I'm inserting n elements, then the height of my tree, even in the best case, it has to be at least log n, right? Because I have a binary tree. Every node can have only 2 children. So the height of my tree has to be at least log n. I cannot have a height of less than log n. But I have a bad case where the height of my tree gets really large. And that bad case is actually when the array or the insertions are already sorted or reverse sorted. So let me just show you this bad case. So this is my bad case. Suppose that I insert a bunch of elements in order from largest to smallest. So I'm inserting n, n minus 1, n minus 2, n minus 3, all the way to 1. Now what happens? Originally, my tree is empty, so I just put n as my root. Then I want to insert n minus 1. Actually, let me put it here. I put n as my root. Then I want to insert n minus 1. So n minus 1, oops, actually I had to put it on this side, has to be on the left of n, right? So I have n minus 1 as the left child of n. But now I insert n minus 2. I start at the top, I go left, I see that I again have to go left. So I have n minus 2 here. Now I have to insert n minus 3, and it will be inserted here. And n minus 4, and so on. So I actually get a tree of height n minus 1. and I get a tree of height n minus 1. The height of my tree is linear. So you see, we have a problem here. In the best case, the height of my tree would be logarithmic, but I don't have the best case here. This is actually a terrible case, and the height of my tree is linear. And the opposite case is also similar. So if I insert from 1, 2, 3, all the way to n, I get a tree that looks like this. I have 1, then 2 is its right child, then 3 is this one's right child, and so on. And it goes all the way to n. And this is also a terrible tree, because all of our runtimes dependent on the height of the tree. So in the next session, we're going to talk about how to keep our trees balanced and how to make sure that our trees have a height of O log n. Okay. See you next week, and happy Chinese New Year.